Oh, sorry.
All right, guys. Everybody good with long division, synthetic division? Good. Okay, it really isn't bad. It's easy to make careless errors. It's easy to forget the zeros. Believe it or not, other than forgetting to put zeros in, the biggest mistake I see when you start actually doing these problems is copying the problem down wrong. Literally, you'll be solving these polynomials that might be 5 or 6 term polynomials. And when you go to actually put the numbers in to do the synthetic division, it'll be a -2 and you'll write +2. And then for the life of you, you can't figure out why this is not working. And that truly, other than occasionally forgetting to put a 0 on a missing powered term, that is the single most large question. So remember that. What we're going to be doing over the next few days is learning how to solve. And I mentioned this yesterday. I said, what happens when you get a 0 remainder? It meant that thing was a factor. And factors, we've been factoring for a couple of years, right? You factor, and those factors give us solutions. So when we're trying to solve a giant equation, we're going to need to factor it. But what we're going to do is be using those synthetic divisors or solutions. And if they divide evenly, we know there were solutions. But you're never going to get them to divide evenly and get zeros if you copy the problem down wrong. And that truly, remember that if you're like, man, nothing works, it's supposed to work, I bet you very likely may have the problem copied down wrong. So anyway, could y'all shut that back door? Do what?
Did you start the video?
Yes. Okay, thank you. So today we're going to be talking about a couple of things. And again, I'm doing this to kind of give you all the tools you need to be able to go and actually start solving these systems. But there's a couple things I want to throw out to you first. Okay, so I'm going to do this by we're going to kind of figure this out as we go. But what if I were to say, determine the remainder. I want you to learn from this. Determine the remainder when x cubed minus 2x squared plus 4x minus 5 is divided by x minus 4. So tell me what you would do to determine the remainder when I divide that polynomial by x minus 4. So you would use synthetic division using a what? Like what number were you going to divide with?
4.
With 4. Right? Because if that's a factor, I could do long division with x minus 4, but it's a power of 1, so I could use a +4 and divide in there, right? Into what? 1, -2, +4, -5. So let's see if I can find the remainder here. Drop the 1 or add the column. 4 times 1 is 4. Add the column is 2. Multiply is 8. Add the column is 12. Multiply is 48. Subtract the 5 is 43. So what do I learn from this? What is the answer to this question? 43. 43, right? Not 43 over x minus 4. That's part of the polynomial result you get, but the remainder is just that number. So what is the remainder? 43. Now, let me just show you something else. What if I took this expression and rewrote it as a function? So I'm basically just tacking an f of x on it. Tell me what you get when I find f of 4. Oh, let's see. 4 cubed minus 2 times 4 squared plus 4 times 4 minus 5 is what? 64 minus 16 times 2 is 32 plus 16 minus 5. So that's a 32. That's an 11. 43. Now, what if I told you that wasn't a coincidence? That the value I get by just evaluating the function at 4 is the same as the remainder I get when I divide that expression by 4 synthetically, what do you now have in your toolbox? Do what? 2 ways to find a remainder, right? The obvious way is by dividing, but that means you can always find a remainder also by just taking the number and plugging it into your function. Now let's go one step further. What do you also now have? I also now have 2 ways to evaluate a function. I mean, if I say find f of 1, find f of 7, find f of 10, you're programmed to plug the number into your equation, right? Well, now you have another way. Now you may go, why wouldn't I want to do this? What if it's a massive polynomial with huge powers or really ugly expressions? If you can take that and do synthetic division with it, it might work out nicely. All right? This thing right here is called, this whole idea here, not that I asked you on a test, what is this? But this whole idea is the remainder theorem. Okay? Well, the remainder theorem. And the remainder theorem basically says, hey, there's 2 ways to find a remainder, but this also means there's 2 ways to evaluate a function. And if you start to find a remainder and you go, man, this is going to take me forever, remember that you can also find that remainder another way. Or if I said, hey, find f of 17,000, and you're like, crud, I don't want to find f of 17,000. Well, maybe dividing synthetically with 17,000 might be better. I'm going to give you a couple of problems in a second. And usually they throw up a red flag. As soon as you start to work them, you go, wait a minute, this is going to be filthy. You don't like filthy, right? So remember, you have 2 options. I'll show you in a second. But now, also, what if this exact problem, instead of having a -5 right there, just stay with me. Instead of having a -5 right there, which means instead of having a -5 right there, all right, what if I instead had a -48 right there? So I drop a -48 down, and I have a -48 right there. Then what happens right here? I get no remainder. Are you with me? And I also end up getting, like we said, 64 minus 32 plus 16 minus 48. Well, that's a 32. That's a -32. I got 0 over here also. And what did we say earlier? That if I ever got a 0 remainder, what did that mean? That this right here was a factor. And that would also mean if x minus 4 is a factor, what is 4? A 4 is the what of that factor? Some of you don't know this terminology, okay? So you remember how, yes, if you said 0, it's a 0 or a root or a solution, okay? Remember how you've been doing problems like this forever, right? Where you go and you factor, right? Those are the factors, right? But the solutions you get, those are the roots. Your calculator calls them zeros. Those are the solutions. If they're real, they're y-intercepts, right? So if this gave me a 0 remainder, that meant that that 4, which if you think about it, is a solution of an x minus 4. It's a root of an x minus 4. That's a solution if I was trying to solve that equation. So if this was a big equation, say equal to 0, and I checked 4 to try to see what the remainder was, and I got a 0, I could also conclude, and by the way, this is no longer 43, right? I could conclude, hey, because it went in there, not only is x minus 4 as a factor, but also 4 would be one of the solutions to that equation. But if I didn't want to check with long division, I could do a quick check. Let me just check f of 4. And if I got a 0, I could go, sure enough, f of 4 is an actual solution to that equation, right? If I was trying to solve. which would mean that x minus 4 is a factor of it. Now, I will say this. You know how, like, if I give you a really big number, like 2,753, and I said factor it. Do you know how 2,753 factors? You don't. I don't either. I know how 72 factors because it's smaller. The bigger numbers I don't. So what do we normally do to try to figure out how they factor up? We do a prime factorization. So what do you usually start with? You start dividing a 2 in maybe to see if it goes in evenly, or maybe you divide a 3 in. And every time I divide a number in that gets a 0 remainder, what does it do to the number? Makes it a little smaller. And eventually we get it small enough we're like, oh, I'm down to 25. That's just 5 times 5. Or, oh, I've got it down to 8. That's 2 times 2 times 2. And we finally get it shrunk. That's what we do on polynomials. We have this huge polynomial that I don't know how to factor. Now, listen, there are some 4-term polynomials that I can factor. There are. And we've learned that, right? Split them up into 2 and 2. Maybe it's a 3 and 1. We've learned some strategies. But those also factor up the way we're going to do it today or in the next few days. So bottom line is, here I might be able to check and see if it's a root. Yep, 4 is a root. It's a solution, which means x minus 4 is a factor. But the problem is I never shrunk down this polynomial, didn't I? But if I were to divide evenly, what do I have left? I have a smaller polynomial than this. So if I'm ever trying to solve the entire problem, what I like to do is synthetic division, because I can divide it in there. And if it works, great. I've got my first of 3 solutions. And if I can shrink this thing down small enough, then I could use the quadratic formula to solve. I can solve for any root that way. Right? So if I can just get it down to a quadratic, I'm money. Problem is, how do I get it down to a quadratic? I've got to figure out some of these roots. Well, that's what we're going to be heading towards. But if all I needed to do is check to see if one worked, you got 2 options. Synthetically divide, see if I get a 0 remainder. Plug it in and see if I get a 0 value. Both of them are 2 ways of doing the same thing. This one I'm talking about is called the factor theorem. If you want to check to see if it's a factor, see if you have a 0 remainder. And since the remainder theorem says there's 2 ways to find a remainder, you could also check to see if you get a 0 y value when you plug a 4 in. So these are 2 ways of doing the same thing. Let me give you an example of how one might be better than the other. Check it out. And notice I'll set you up for failure with my wording. Who is going to rise above that challenge? Here we go. What is the remainder when this is divided by x minus 1. So what's the remainder when that's divided by x minus 1? Now, if you're programmed to divide when it asks for remainder, then you've got some work ahead of you. Because according to synthetic division, you're going to have to take the divisor of that, or the root of that, which is 1, and then you're going to need all the coefficients and the constants, right? You're missing a lot of terms. There's my 2 for 27. There's my 0 for 26, 25, 24, 23, 22. There's my negative 3 for 21, 20, 19, 18, 17. There's my negative 5 for 16, 15. There's my 4 for 14, 13, 12, 11, 10. There's my 6 for the 9, 8. There's my negative 2 for the 7, 6, 5, 4, 3, 2. There's my 4, and there's my constant. Have fun, right? Now, I'm not saying you can't do it, but I can tell you in the entire history of me giving a problem like that on the test, very, very, very few people get that right doing it this way. And the main reason is I'm not usually this kind. I'm usually this kind. Now, I do that as a gift to you. I truly want you to go, what? There's no way I can actually get this done in the space that I have. So I'm trying to trigger for you, oh, wait a minute. There's another way to find this. Okay? And the other way to find it is not by synthetic division. It's by what? Just evaluating the function at 1 and treating this like a function. Now, as you can imagine, I'm going to have to probably pick really clever numbers, right? 1 and -1 are always great ones because when I plug a 1 in there, what's 1 to the 27? And it doesn't change that value. When I plug a 1 in there, what do I get? Times -3. When I plug a 1 in there, what do I get? -5, and then +4, and then +6, and -2, and 4, and 3. Nothing really happened here, did it? So I am able to really clearly go ahead, type that in there, clean it all up, and get 9. And there is happiness in paradise. But if you don't know the remainder theorem, you don't get this. Good luck. Are you with me? You've got to know the remainder theorem. There's 2 ways to find a remainder. Now, a lot of people get this, but then it's amazing how I'll give them the exact alternate universe problem. Here we go. I'll say evaluate f of x, 2x to the 9th minus 16x to the 8th plus 15x to the 7th minus 9x to the 6th plus 17x to the 5th minus 16x to the 4th minus 34x cubed minus 45x minus 1. And then I'll say, what is f of 7? Now, my hope your thought is, are you kidding me? 2 times 7 to the 9th? I didn't memorize 7 to the 9th. I have 7 to the 3rd memorized. No higher. I'm going to be here all day. And more than likely, I'm going to make a careless error. But wait. Not only does the remainder theorem give you 2 ways to find a remainder, but it also gives you what? 2 ways to evaluate a function. Because we just saw that finding f of 7 is the same thing as what? Dividing synthetically by a 7 and keeping the remainder. So if you start to do this and you're like, what? That's going to be terrible. It very likely, you're sitting at a math tournament, my test, whatever, very likely that 7 is going to go nicely into this. So let's just see. 2 is the 9, -16 is the 8, 15 is the 7, -9 is the 6, 17 is the 5, -16 is the 4, -34 is the 3. There is no 2. There's my -45, and there's my -1. Let's see if this problem was just constructed nicely. Drop the 2, multiply 14, add -2. So far, so good. 7 times -2, -14, +1. So far, so good. 7 times that's 7, add -2. My numbers are staying pretty small. 7 times that's -14, 3. 7 times that's 21, 5. 7 times 5 is 35, 1. This is not getting out of hand at all, is it? Now, you make one careless error. You go -9 times 7 is +2. Now you have 14. Now you got 31. Now you have 217. I mean, it will get out of hand in a hurry if you make a careless error. So when it gets out of hand, go, wait a minute. I bet I forgot a negative or something. 7 times 1 is 7. Yeah, no pun intended. 7 times 7 is 49. And then finally, 7 times 4 is 28. So if my remainder here is 27, then what do I know? My value here is 27. And there is happiness in room 20, whatever this is. What are we in? 5? 4?
4A.
Are y'all with me? Now, I am telling you, I put these 2 problems that I just did on your test every year. When somebody tells you that, what should you do? You should circle it, put a star, and say, man, know this.
204.
204? You know, I spent 18 years in the same room in 225. And I thought, man, I'm going to retire in 225. And then this room opens up right next door that has all these windows. I was like in an internal room, no windows. I was like, who needs windows? And then I looked through those windows and I'm like,
I can't imagine.
so I moved over and I'm like, now I'm never going to leave. And I stayed in there for like 8 years. And then in the last 3 years, I've been in 4 different rooms. It's like boom, 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 boom. They kept tearing my room up, or they'd find asbestos in it, or my classes were too big and they'd shuffle me off somewhere else. Anyway. Are we good? By the way, every now and then I'll have somebody do this. All right, so my answer, and they circle the polynomial that goes with this. Like they come in here and they go, all right, my answer is this. All right, they fill it all in, write it over the x, whatever that is, minus 7. Guys, the answer is not the polynomial. Remember, the question was, what is this? So remember, when you do long division to find the remainder, to use it as your value, go grab that and use that as your answer. Are you with me? Okay. So anyway, nice there. Also, do you know, for instance, if I were to ever give you, say I gave you this problem right here. Are y'all aware that if this is a big equation and I were to say solve, do you know how many solutions I'm going to have?
Is it 8?
I'm always going to have this many. Now, that doesn't mean that the 8 solutions are all unique or all different. They might all be the same. I mean, look, this problem is nice and factored, right? If I multiply that out, it's going to be a really big polynomial, right? But very clearly, what is my answer to this equation? 1. We would say that the answer is 1, and sometimes we call them double roots, triple roots. We would say that this one has a multiplicity of 8, which means there's 8 roots. That multiplicity was actually used on your test at Briarwood. And I'm going to go back and revisit those questions. I have them on one of the reviews we're going to do, because you're going to know how to do all those as soon as we get through this and the little rational functions thing we have. So right here, I don't know what my answers are. I would have to solve, and that's what we're going to start learning how to do. But so you know, when you see a number here, this says that I have 8 total roots. Maybe they're identical, maybe they're different, maybe they're real, maybe they're imaginary, maybe they're irrational. I haven't the faintest clue yet. But when I count them all up, double, triple, whatever, there's 8 of them. Are y'all good on that? All right. And again, you just look at the highest power. If I'm looking at that one, this one has 4 roots if I'm solving. It's going to have 4. They might be the same. They might be different. We'd have to figure that out. Okay. Also, there's something called what we call the conjugate root theorem. Do y'all remember what a conjugate is? Yeah, you do.
It's that thing you look by.
Yeah, like officially, a plus bi would be an imaginary root. And it has a conjugate called what? A minus bi. Notice the a parts didn't change. But those are conjugates of each other. Conjugates always occur in pairs if. So right here, let's just say, I'm going to give you the conjugate root theorem. Again, I'm not going to ask you to say, what does the conjugate root theorem say? You just need to know it. The conjugate root theorem says that if you have a polynomial like this, ax to a big power, bx to a slightly smaller power, cx to a little bit smaller than that power, etc., etc. If all of your a, b, c, if those are real numbers, which means there's no i's in your polynomial, then imaginary numbers occur in conjugate pairs. So why is that significant? Well, it's significant because if I, for example, if I said, hey, you've got this big polynomial and there are no i's anywhere in your problem, if I said if 2 minus 3i is a solution, what else do you know? 2 plus 3i is also. And when is that true?
Always.
Nope.
No, sorry.
When what? If all of those are real numbers. So if you see an I in there, that is not true. It might be true, but it's not a rule. It's not a theorem. It's not a guarantee. So bottom line, imaginary numbers, people just, like if I were to go right now and ask any Algebra 2 student in a regular Algebra 2 class at the end of the year, I could probably say, imaginaries always come in what? Conjugate, and they go pairs. And I'm like, it's not true. Yeah, it is. No, it's not. Except in Algebra 2, they don't give you polynomials that have i's in there. So, but they do in Math Teamville, right? They're always changing little bitty details or seeing if you're checking that stuff. So imaginary numbers do generally occur in conjugate pairs. They do. But in the problems we deal with, we see everything. So you got to know, yes, they occur in pairs, but only if, or they're guaranteed to occur in pairs, but only if those numbers are real. Now you can extend that knowledge. You can extend that a little bit as well and say, okay, technically, these are conjugates. They're imaginary numbers. But you can also kind of think about conjugates when they're not imaginary with irrational numbers. Like, what if I were to say, and I'll kind of fill all this in lovely pink. Here we go. So it also works for stuff like, I'm just making something up like x plus y root a. Say I didn't have an I in there, like I'll just give you but that would mean that x minus y root a. So it doesn't have to be imaginaries, even though from what I have read, conjugates are referring to imaginary values, but it's also true when you have irrational numbers. So irrational numbers, not imaginary, irrational numbers also occur in conjugate pairs. If what? Not if they're real, but if they're what? Guess. If all your A's, B's, and C's are rational. Which means you just don't have square roots in your problem. And guess what? 99% of the time when you're given a polynomial, these are integers. 2, -4, 6. So both are true. They're going to occur in pairs. But should you ever look at a polynomial and you go, wait a minute, my A value is 5i. My C value is 2 root 3. All bets are off. They might occur in pairs. They might not. But you're going to see the value of knowing that they occur in pairs like this. You're going to see that because you're going to have to solve these. And the second you see that one of them roots, you're like, sweet. Not only do I have one, I have 2 of them. And you're going to have to find these, remember? Because I'm going to give you a big polynomial. And every time you find one and divide it in, what does it do to the polynomial? Shrinks. So the more you have, the more you can shrink it. And when you finally get it down to a quadratic, we've got rules to solve any quadratic. You kind of see where we're going with all this? Okay. Last thing. Think we have time? I think we do. Descartes' rule of signs. All right. Now, you may have heard of Descartes before. Anybody?
Descartes? Like R-E-N-E?
Yeah, Descartes. Everybody says Descartes or whatever.
Doesn't he have like the theorem that
I think
it's logical thinking?
I don't know that.
It's
actually.
like if monkey like banana and I like banana, I'm monkey. That kind of thinking.
Yeah, I don't know the philosophy side of him. I did hear that he did a lot of different things. But in terms of math, have you heard of the Cartesian plane? Cartesian plane. So the XY coordinate plane, a lot of different things were attributed to him.
It is Descartes.
You what?
He did say, I think before him.
I think they're fine. Yeah.
He decided he was going to question everything, and then the only thing he found that he couldn't doubt was that he was thinking, because if he wasn't thinking, then you.
Yeah, I'm all in circles now. Yeah. Hey, all right, focus. Now, Descartes came up with this rule of signs. Now, this rule of signs, Descartes, and listen, I do not value this much. I'll show you where I do value it. But you're going to be asked this on a test. Every now and then it is important at a math tournament because they'll ask you a question that you need this for. But Descartes' rule of signs, he came up with a way to look at a polynomial and look at its signs, whether it's plus, minus, the pattern of the signs, to tell how many positive, negative, or imaginary roots a problem could have. Problem is, his results aren't conclusive. They're kind of like, okay, I have evaluated this polynomial, and I know that I could have 4 positives, 3 negatives, and 4 imaginaries. Or, and there's so many ors, it's like, seriously? There's 10 different results you came up with? That's not overly helpful. And you'll see this, especially on the problems we do, where rarely am I given polynomials bigger than x to the 4th. I don't have to find many. But I suppose if I had a polynomial that was x to the 20th, and I had to find 18 roots, that maybe doing what he did was helpful. But let me show you what he did. So Descartes, or Descartes, or whatever you want to call it. All right, Descartes noticed this. I'll do this one. Let's just say I have a function. And again, I have not studied or read about why all of this works. I have looked at some shifts as I shift the graph up and down, what it does to the roots. And I imagine that's probably what he was doing, although it must have been really hard for him because he didn't have a graphing calculator to check those shifts. So he may have done something different. I don't know. But this is what Descartes noticed. When I initially look at a polynomial, now granted, this is a function that has, if I were to graph it, crosses through some x values, some negative x values, and I could do the same thing if this was a 0, okay? I could do the same thing. But if I'm thinking about it as a function, if you look at this problem and you look at these signs, all right? So look at the signs. There's a plus, a minus, a plus, a minus, and a minus. He went through and he counted how many times the graph switched from plus to minus or minus to plus as he went through from left to right. And you can see that this thing switched 3 times. Are you with me on this so far? So when I initially counted, I got 3. 3, sort of, is the number of possible positive roots I could have when I solve. Now here's what gets ugly. Or anything less than that. But wait, I know. But wait, because imaginaries have to occur in pairs, and you'll see why this in a second. I can't have 3, 2, 1, or 0. I can only have 3 or 1. So bottom line, whatever number you find, decrease it by 2 until you run out. If I counted 8 changes, that means I can't have 8 or anything less, because if I just decreased by 1, that would give me an odd number of imaginaries left over. That doesn't work. Imaginaries have to occur in pairs because all of my numbers are real, right? So what ends up happening is whatever number you get, I decrease it by 2 until I can't have negative number of roots, right? So I just decrease by 2 until I run out. If that had been a 5, 5, 3, 1. If that had been a 4, 4, 2, 0. Now, then he did this. Then he goes back and he goes, hey, what if I figured out what f of negative x was? Now let's think about this for a second. There's an easy way to do negative x. The easy way to do it is anything that has an odd power, change the sign. Why does that work? Think about it. What is negative x to the 5th? Negative x in parentheses to the 5th would just be negative, right? So it's going to change the sign of that and give me this. But what's negative x to the 4th? Positive x to the 4th, right? So that doesn't change the sign, does it? So it stays negative. What's negative x cubed? Negative x cubed times the negative 2 changes the sign. What's negative x squared? Positive x squared, no change. Negative x times negative 4, positive 4x. I can't plug anything in there. So when you go back and look at this, look, all I really did, I don't even write that anymore. My keys might not even have this. All I do is look at the odd powers, change the sign, keep it, change it, keep it, change it. That's a constant. So can't do anything with that. It stays constant. And then what did he do? He went back and counted again. So he went back and went, well, negative to negative. If I look at these signs right here, how many times do I switch from plus to minus or minus to plus? There's a minus to plus. There's a plus to minus. So twice. Twice is the number of possible, take a guess, negative roots I could have. And if I got a 2 or anything less than that. But wait, I can't go 2, 1, or 0, because if I went 1, you'll see in a second, then I would have an odd number of imaginaries. I can't have an odd number of imaginaries. They always occur in pairs. So 2 or 0. Now I'm going to talk about this in a second. You're going to have to do better than what I wrote right here. Then the last thing he did was, well, wait, how many total roots do I have on this problem? Now, how do we tell how many total roots we have?
5.
We look at the highest power, right? So if I have 5 roots, and think about it. If I have 5 roots and 3 are positive and 2 are negative, is there anything left over to be imaginary? So the number of possible imaginaries, initially my thought, imaginary roots, initially is 0, but this is where it gets tricky. Wait a second. He said that I could have 3 or 1 positives, 2 or 0 negatives, and initially I'm thinking 0, but wait a minute. What if there were 3 positives and no negatives? Then what would I have? I would have to have 2 other roots. They must be imaginary. But wait, what if I have 1 positive and 2 negatives? That would also go with 2, wouldn't it? And what if I have 1 positive and no negatives? Then I'd have to have what? 4. And if you're not seeing this, remember, your roots are going to be either real or imaginary. If they're real, they're going to be positive or negative. So the options are there's positive roots, there's negative roots, there's imaginary roots. The total has to add to 5. Well, if I do what I just said here, this looks terrible. Because how do I know which lines to follow? I have no idea. So don't do this. This is what you need to do. What you need to do is go, all right, whatever I get, I'm going to get rid of all this. Whatever I get for positives, for negative roots, which was 2 and 0, put that 2 and 0 with each option. And that way I can see, 3 positives and 2 negatives would have how many left over to be imaginary? None. 3 positives, no negatives would have how many left? 2. 1 positive, 2 negatives, 2. And 1 positive, 0 negatives, 4. And now I can clearly see what your options are. Now you can do it this way, or you can do like the book does. The book says positive, negative, imaginary, and they just list them. 3, 2, 0, 3, 0, 2, 1, 2, 2, or 1, 0, 4. And you can list them like that, but most people would rather do this. Y'all with me? Let me give you one more and run through all this, and I think we'll be good if we can do this. And you can do most of your homework with this. Okay, and this will also help you with this last thing I want to talk about. What's a good one? How about this? And I'll say, hey, we're going to be yeah.
If you were doing like the number of roots and there was like 1 switch, would it be 1 and 0 would be the possibility?
No, good question. No, you always decrease by 2. 1, if I decrease by 2, that's negative. Can't do it. So just write 1. Yes. Yeah, you don't always end with 0. Odds end with 1, evens end with 0. All right, so let's check this out. How many signs? And by the way, I want you to notice something. I have every power represented, don't I? And what are the signs doing? Changing. Remember that. Because I got news for you. What I just found from Descartes' rule is garbage. That result is not going to help me solve this thing. And you're going to see that Monday and Tuesday. But watch what this tells me, okay? Check it out. How many times do my signs change? Ooh, plus to minus, that's 1. Minus to plus to minus to plus to minus to plus. That's a lot of changes. In fact, that's 6. So the number of possible positive roots is not just 6, but maybe what? 4, 2, or 0? Now, here's your moneymaker. Number of possible negative roots. Check it out. What did we say you did to find these? You changed the signs of your odd, right? And what do you see? They all end up being what? So how many sign changes do you have? None. Was that helpful? Darn right it's helpful. And you're going to see this later. You're going to learn that there are only certain numbers that could possibly be roots given a polynomial. And sometimes there's 50 options. And you're like, wait a minute, there's 50. Sometimes there's 100 options or more. And you're looking at it like, how am I going to check 100 terms? Well, I'm not going to give you one like that. Let's just say there were 18. How am I going to synthetically check 18 terms? Well, guess what? All of those answers that you have, it's like plus or minus 3, plus or minus 7, plus or minus 1, plus or minus 2. What have you just learned? Half of them are gone. There are no negative roots. So you wouldn't have to check any negatives. So if you remember in your head, wait a minute. So you're saying if I have alternating signs up here, when every power is present, that means that all my answers are going to be positive? Positive or imaginary? Yeah. No negatives. Are y'all with me? Now, how many imaginaries? Well, there's 6 total. So if there's 6 positives and no imaginaries, then what? No negatives, there's 0. But if there's 4 and 0, then there's 2. And if there's 2 and 0, there's 4. And if there's none, there's all imaginaries. All right, last quick thing just to show you. Right here. What if all your signs are the same to start? What if everyone starts out positive? Then what? There are no sign changes. If they're all positive, nothing changed. So what is your number of possible positives? 0. That's helpful. So I gotta be honest with you. I'm gonna make you do Descartes' rule once on a test. After that, do it when you feel like it. But I'll tell you, when I do it, if I look up and I see all the same sign, then it's worth acknowledging it because that cuts down on my checks. If I look up and I see all alternating, it's worth doing it. If you forget to do it, you still get it done. You just might have to do a little bit more synthetic division. Hey, do the best you can on this. There might be a couple questions I didn't quite get to, but if I do, no worries. Circle those. We're going to jump all into that in the next couple days.
Oh, there's no positive. All the time you say there's no positive. If I get this positive, there's positive. Yeah. Yes. Yes. Weird. Okay, you're starting.
So, like, why? I don't understand.
Yeah, it's not.
So on the test, would you specifically say use Descartes' rule?
Yes, and I wouldn't even ask you to solve. I'll say, what would Descartes' rule say about the possible number of positives, negatives, and imaginaries?
Okay.
Yeah, and you'll see that tonight, I think. What's up, man?
She wants to go on. So now it's just like,
Nate, where did you go?
The whole car.
So over the doctor, that's.
So funny.
Why did you come?
Just a hurry, because,
Jackson
says don't get stuff recorded.
Ooh, I already recorded. Thank you, though.
It could have been like